Oh, hi again. It's so good to see you. I'm Reggie. And I'm Byron. And I'm Blueberry. And I'm Hans. And today, we are going to learn about rate situations and rate tables. We're also going to learn about ratios. They could be very confusing, but don't worry. We will try to go over this as basic as we can because we explain things to you and that's how we learn. And I know specifically what pages we're going to do today. We're going to do 9, 10, 11, 13, and 30, and then we'll be done for the day, okay? All right. Find the totals so far. Noreen started to save money. Every day she puts 3 $1 coins into her coin bank. Write how much money she had each day. Okay. So, what should we do here? Well, obviously, we have to skip count, and we need to find how many coins she keeps putting every single day. Now, of course, Noreen began with an empty bank, so it's no surprise here that there are 0 coins. Noreen began with $0 in her bank, because 0 times 3 is 0, so that's obvious. But when we go to this one, it starts to kick up. On day 1, Noreen put $3 into her bank. Well, that's obvious. 1 times 3 is 3. Plus, how many coins do you see there? 3, right? So, $3. Let's see if I could do this. On day 2, Noreen put $3 into her bank. Okay, so on day 1, Noreen put $3 into her bank. On day 2, she put $3 more into her bank. 3 plus 3 is 6. So that's $6 in her bank. That's right. On day 3, Noreen put $3 more into her bank. I can figure this one out. 6 plus 3 is 9. $9 in her bank. That's right. On day 4, Noreen put an extra $3 into her bank. How much money is in the bank now? Well, 4 times 3 is 12, because 3 plus 3 plus 3 is 9, plus 3 is 12. So there are $12 in her bank now. And if we keep doing this, we will just keep adding 3s forever. So it's basically just adding 3s. On day 5, if Noreen put 3 extra dollars into her bank, then it will be $15 in her bank. $15 in her bank. Excuse me. Because 12 plus 3 is 15. And on day 6, Noreen put 3 more into her bank. That would be 18, because 15 plus 3 is 18. It's kind of like a pattern, pretty much. Every time we go to a higher amount of days, there are a higher amounts of money being added. 0, 3, 6, 9, 12, 15, 18. Very cool. Yes. Wait a second. Day 10, day 12, Noreen continued to put $3 into her bank every day. How many dollars would Noreen have on day 10? Let's see. On day 6, it was $18. So that means on day 7, it should be $21. Wait a second. I think I noticed a pattern. I think we should multiply the day number by 3 to get the answer. Day 10. 10 times 3 is 30, so I think Noreen put $30 in her bank, right? Yes, you are correct, because 10 times 3 is 30. That's a little handy. But what about on day 11? Let's think. Well, on day 1, she puts $3 into her bank, which obviously makes $3. But 10 plus 1 is 11. So 30 plus 3, $33. That's right. Which means on day 12, Noreen had $36 in her bank. That's right. Wow, you're getting the hang of this. Doesn't look like a table to me, though. Well, when we turn to the next page, it will definitely look like a table now. Look! Wow, that's so cool. This rate table shows Noreen's savings. So, no wonder we had a repeating pattern. On 0 days, she got $0. But on 1 day, she got $3. In 2 days, she got $6. In 3 days, she got $9. And on 8 days, she got $24. What did you notice? What do you notice about these? They keep adding by 3. Wait a second. 3 plus 3 is 6, plus 3 is 9. So we just keep adding 3 to figure out how much money Noreen has each day. It's a repeating pattern. That's right. And repeating patterns are usually easy to see in math, but not too easy to understand, so you better clear them out. Now for over here, it's the same thing, except with a different person. Let's do a different scenario. Let's say Ned put $2 in his bank every day. That would mean that in day 1, he would get $2 in his bank. In day 2, he would get $4 in his bank. On day 3, he would get $6 in his bank. What do you notice about this one? Ooh, they keep adding by 2. That's right. We keep adding by 2 to see how much money Ned saves in his bank. Very cool, huh? We could see more rate tables like this. However, they are not all the same because when you think about it, some have different repeating numbers, and that is kind of like a problem. So, when we want to identify if it is a ratio table or not, we want to check to see that all of the numbers are exactly the same. 4 plus 8 is 12, plus 6 is 18. 8 and 6 are different numbers. So that tells me it is not a rate table because a rate table has to be equal. 1 times 4 is 4, but 2 times 4 is not equal to 12. It's equal to 8, so it's not equal. That's why it's not really called a ratio or rate table, because the numbers are different every time. But this one is a ratio table because we keep adding by 7 every time. 7 plus 7 is 14, plus 7 is 21, plus 7 is 28, plus 7 is 35, plus 7 is 42. 1 times 7 is 7, 2 times 7 is 14, 3 times 7 is 21, 4 times 7 is 28, 5 times 7 is 35, 6 times 7 is 42. And plus 1, 2, 3, 4, 5, 6. See? Very easy. And of course, this is also not a rate table. Look at this one. 3 plus 2 is 5, plus 0 is 5, plus 4 is 9, plus 2 is 11, plus 3 is 14. 1 times 3 is 3, but 2 times 3 is not equal to 5. See, it's equal to 6. So that's not a rate table as well. So number 14 is the only real rate table. These two hypothetical rate tables aren't actually rate tables because we keep adding different numbers instead of the same number every time. And that is where we're going to get to the next concept about ratios. But first, we need to understand what unit rates and constant rates are. Equal groups, multiplication, and rates. A rate problem can be thought of as an equal groups multiplication. The multiplier is a unit that counts the number of groups. The unit rate is the amount in one group. Oh, I see. So, the number of equal groups times the amount in one group equals the total. The multiplier times the unit rate is the product. And the number of days times 4 snails each day is the total number of snails so far. I like the snail scenario. If the same rate is repeated, the rate is a constant rate. There are special words that show a constant rate, such as every, each, and per. The rate is 4 snails every day, the rate is 4 snails each day, and the rate is 4 snails per day. No matter which word you use, they are exactly the same thing. Yeah, so it's pretty easy. But then we get to the more complicated concepts, where we actually see why the rates are equal in the first place. We look into something called ratios. Discuss which are ratio tables and why. Tell ratio stories for each ratio table and tell what the linking unit and the column labels are for each story. Hang on, before we go any further, we need to figure out what a ratio is. Yes, you're right. A basic ratio has the least possible whole numbers. 4 to 7 is a basic ratio because no whole number, except for 1, divides evenly into 4 and 7. But what is a ratio in general? Oh, a ratio is basically a number, a colon, and another number. Oh, I get it. This number 4 shows the first one, and 7 shows the second one. 4 is the first one there, and 7 is the second one there. And the dash that splits the two numbers in the middle represents the colon in a ratio. That's right. That's totally correct. So, it's the same thing for these ratio tables, except the numbers have to be exactly the same. So, let's double check. 4 plus 4 is 8, plus 4 is 12, plus 4 is 16, plus 4 is 20, plus 4 is 24, plus 4 is 28, plus 4 is 32. Yes, that side's good. But is the 7 side good? Because if it's not a ratio table. 7 plus 7 is 14, plus 7 is 21, plus 7 is 28, plus 7 is 35, plus 7 is 42, plus 7 is 49, plus 7 is 56. So, yep, the 7 side is good too. This is a ratio table because we keep adding 4 and 7 together. But what about this one? I'm not so sure about this one. 3, 6, 9, 12, 15, 18, 21, 24. Okay, the 3 side is good. But I'm not so sure about the 5 side. What do you notice about this side over here? 5, 12. 12. 5 times 2 is not equal to 12. It's equal to 10. So, nope, it is not a ratio table. Plus 5 is not equal to 12. 5 plus 5 is 10. So, this is not a ratio table. Oh, I get it now. And also, if you look really closely, bigger ratios like 8 to 14 can be equivalent to smaller ratios like 4 to 7. Because 4 times 2 is 8, and 7 times 2 is 14. So 4 to 7 and 8 to 14 are equivalent ratios, or basically ratios, that are made up of multiples of the basic ratio row. Equivalent ratios are written as 18 to 14 equals 20 to 35, or 8 to 14 is equal to, with the colons, 20 to 35. Yes! So, that is very cool. And, trust me, it will get easier as we go along. But not always. These are kind of the same thing, too. Oh, what are these? Oh, that's right, equivalent ratios. Duh. Anyways, let's see. 3 to 7, 6 to 14, 9 to 21. Are they equivalent because 3 plus 3 is 6, plus 3 is 9, 7 plus 7 is 14, and 14 plus 7 is 21. That's right, Reggie. Wow. Good job. Anyways, yeah, that's why they're equivalent. Because we keep adding 3s and 7s all the time. Great job, Reggie. I can see you're already solving this. Well, let's go to one last page. That's odd. We have something missing. C. 6 to 14 is equivalent to C to 35. Two equivalent ratios make a proportion. Any two rows from a ratio table make a proportion. In a proportion problem, one of the four numbers is unknown. Solving a proportion means finding that unknown number. Let's see over here. So, if we look at this ratio table, R is 6 and Y is 14. Now, remember, this time, this is different because we keep multiplying by 2 now. 6 times 2 is 12. 14 times 2 is 28. But this proportion ends in 35. So we need to find the one that ends in 35, which traces to something I like to call a factor puzzle. You already learned about factor puzzles because we already reviewed them in a video. If you want to see it, click on the first 6th grade video on our math playlist. Anyways, 2 times 3 is 6. 2 times 7 is 14. 5 times 3 is 15. 3 times 5 is 15. 7 times 5 is 35. And 2 times 7 is 14. So, in a factor puzzle, you learned that this has to be the same as this. So this has to be the same as this. So what is the missing value? 5 times 3, which is 15. So C equals 15. Wow, that's so interesting. Yes, you can solve a proportion by just looking at a ratio table and a factor puzzle. These can really help you figure out missing numbers in ratios. Anyways, that's it for us today. I hope you enjoyed the video. We will see you later in the next math video. Remember, stay curious and continue to solve more math mysteries with us. I'm Blueberry. I'm Hans. I'm Byron. And I am Reggie. And we are all here to say, see you again next time. Woohoo! Do